Hi everyone. I'm addressing your feedback today on the lecture on Hess's law. First question I had is, if Hess's law says that the delta G of a reaction is equal to G1 plus G2, then how is it also true that delta G reaction is equal to G final minus G initial? Okay, so you're correct that in general, for any change in a particular variable, it should be the final variable of that, final value of that variable minus its initial value. And that is true. What you had written on the feedback sheet was this. This is actually not Hess's law. There's a subtle difference here, but it's an important difference, which is this shouldn't be the delta G of a reaction is equal to G1 plus G2. Hess's law says that the delta G of a reaction is equal to the change in free energy for one reaction plus the change in free energy for another reaction. This is talking about an actual value, like the absolute value, like just how much free energy a substance has. This is talking about the change in free energy that a substance experiences as it undergoes some particular chemical or physical process, like if it's converting from something into something else. What I will say is that these two expressions, those are equivalent, and I'll show you how they are equivalent. They are equivalent because G is a state function. So let me show you an example of how this could work. Suppose I have some reaction. A reactant A converts into two B molecules, and then those two B molecules convert into three C molecules. Suppose then that the delta G for this reaction, I'll call delta G1. The free energy change for this reaction, I'll just call delta G2. Now, my question might be, what is the free energy change? A question that that Hess's law can answer is, what is the free energy change of the reaction A converting into 3C? So I can create this reaction. I can propose a way of going from A to 3C by, in one step, I could propose an alternate reaction where I do this in two steps, two reactions. First A goes to two B molecules, and then two B molecules convert to three C molecules. Basically, add these two guys together. So I have that A plus 2B goes to 2B plus 3C. And then we can note that, okay, the two B's are on both sides of the equation, so they'll cancel each other out, and that will get me my net reaction of A converting into 3C. And I just added these reactions together, and so Hess's law tells me that I can just add together their free energy changes, delta G1 plus delta G2. So this is me just applying Hess's law. Now, how can I show that this Hess's law is going to give me the same conclusion as this expression of the free energy change? So let me write what the free energy changes are for each of these reactions, and then I'll add them together, and we'll see that we get the same thing as we would have if I was just looking at final minus initial. Delta G for the first reaction should be the free energy of my final state minus the free energy of my initial state. So this should be G, the free energy of two B molecules minus the free energy of an A molecule. So that's again final products minus initial reactants. For delta G2, it's going to be the free energy of three C molecules minus the free energy of two B molecules. Now I'll just add these free energies together, and I'll get, well, we'll see what we get here. So I predict then that the delta G of this reaction should be G of 2B molecules, minus the free energy of the A molecule plus the free energy of the 3C molecules minus the free energy of the 2B molecules. And what we can note here is, just like in the chemical equation, in the mathematical equation, the free energies of my 2B molecules cancel each other out. Here I'm adding in 2B and then I'm subtracting off the free energy of the 2B molecules. So what I'm left with here is the free energy of 3C molecules minus the free energy of the A molecule. So I get that the delta G of the reaction is the free energy of 3C minus the free energy of A, which is the same expression I would get if I were just writing the delta G of this reaction, products minus reactants. Free energy of the 3C molecules minus the absolute value of the free energy of the A molecules. So again, I get the exact same thing as I would have before. So I hope that addresses your question. Partly it's that these two expressions are equivalent to each other. How can they seemingly be different? Partly it's because they aren't different. They are the same equation. There is also some confusion here of how you actually express Hess's law, which is in terms of changes in the free energies of various reactions. The next question here was, what other reactions can be solved using Hess's law? Any reaction. So we can look through some other examples of this, but as to give or next week, but to give you kind of a preview of where we're going, you can use Hess's law to calculate the free energy change of any reaction by looking up delta G's for other reactions. The way this is normally done is you might have a particular reaction. A reaction, say, for the combustion of glucose, C6H12O6 plus 6 oxygen molecules going to 6 CO2 molecules plus 6 water molecules. And let's say I wanted to calculate the free energy change of this reaction. I will use sort of a combination. They are equivalent, but I'm going to kind of use Hess's law and our just general understanding of changes in a state variable as being the final state minus the initial state. I will tell you that you can calculate the free energy change for this reaction in terms of what I will call free energy changes of formation of your products minus the free energies of formation of the reactants. So again, I'm going to talk about this in more detail on, I'll probably do it either, if not next Monday, then on next Wednesday. But free energy changes of formation, these are tabulated in large data tables. There's one in the back of your textbook. But basically, they describe the energy of creating a molecule or any chemical compound from its individual elements. So how much free energy, for instance, do you get when you form 6 carbon dioxide molecules? So, or just when you form carbon dioxide molecules. So I would say, if I wanted to form carbon dioxide, I would take carbon, probably in the form of graphite, react it with oxygen, that will give me carbon dioxide, the free energy change for this reaction we will call the free energy of formation of carbon dioxide. For water, water can be created by reacting a hydrogen molecule, or 1 mole of hydrogen molecules, with half a mole of oxygen molecules. That will get me H2O, and then the free energy change for this reaction we will call the free energy of formation of water. And similarly, I can do another one here for glucose. To make glucose, you need 6 carbons, you need 6 hydrogen molecules, and you need 3 oxygen molecules, and that will give you a mole of C6H12O6. Each of these substances, each of these molecules has a certain amount of free energy that's released or absorbed, for that matter, when you create them from their individual elements. And so what is sort of going on under the hood here is you imagine an alternate reaction pathway. Hess's law is all about finding alternate reaction pathways that will give you a certain net result that might be a single reaction that you're interested in. So I can imagine a reaction pathway where first I deform, I break down the reactants into their individual elements. I break down a molecule into its individual elements, so I would need to spend some free energy there, that's why it's negative. Then I can take those elements and reform them as actual molecules and reform the products. So there's going to be entropy and enthalpy changes and free energy changes for forming these products, and then you also have to deform or go backwards and break down your reactants into your basic elements before you can convert them into products. So again, this is an analysis that we will do next week. But to answer your original question, what other reactions can be solved using Hess's law? Technically, any reaction, because they all follow Hess's law. I'm still a little confused by reaction coupling. Is adding heat to a reaction to make it spontaneous the same as coupling? That's a really good question, and I don't know if I have an answer that I would be satisfied with. I will hand-wavingly say, kind of. Adding heat to a reaction is kind of like coupling it to make it spontaneous. So for instance, suppose you have some endothermic reaction, like converting simple sugars into caramel. So if you want to make caramel, you heat up sugar, you boil it, and you break down and you react some of the sugars, you convert them into caramels, which is technically itself another class of molecules. Anyway, that takes an inflow of chemical energy, or it takes energy to do that. That's a non-spontaneous process. So you can do that process by coupling it, quote unquote, to another chemical reaction. I tend to think of coupling of chemical reactions as two reactions that are occurring in the same chemical system. If they are occurring, one releases energy and the other one absorbs it, and they're happening in the same chemical system, like all in the same box, all in the same beaker, I would say that those two reactions are coupled in some way. But they don't need to be directly coupled. They could be indirectly coupled. Like the case I was just giving, if I want to heat up some sugar and convert it into caramel, I supply that energy as heat. That heat doesn't have to come directly from a chemical reaction that I'm adding in with the sugar. It could be done indirectly, like I have a propane flame that I'm heating my pot on top of. So that propane flame is providing heat, which is then being transferred into the sugar to get that chemical reaction to go. So you could argue in that sense, okay, the heat is what's causing the chemical reaction for the caramel. But where did that energy come from? That energy came from the combustion of a hydrocarbon, not glucose in this case, but say propane. So in that sense, you could argue that that reaction is coupled, it's releasing free energy, and that causes another reaction to occur. So I guess I would hand-wavingly say that adding heat to a reaction to make it go forward, to make it spontaneous, is one where you couple one reaction with another one. That energy had to come from somewhere. Um, it either came from another chemical reaction, like you're combusting something, or it could be you could provide that through electrical energy, like an electrical current, but then that electrical power originally came from some other chemical or physical process. So they are indirectly coupled. So I don't know if that's a satisfactory explanation, but I hope that that addresses your question. And if it doesn't, please stop by. I would love to discuss it further. Please come by during office hours. Again, as usual, I have open door office policy. I'm always here. Those were all of the questions I had for feedback today. That's it for today. I will see everybody next Monday. I hope you all enjoy your extended break starting Wednesday. Have a happy Easter.